Gravity. Here, let me help. From the University of Caltech. Einstein came up with the theory of general relativity 1915, the prototype of all modern gravitational theories. Its crucial ingredient involving a colossal intellectual jump is the concept of gravitation, not as a force, but as a manifestation of the curvature of space-time.
The reason the bowling ball and the feather fall together is because they're not falling. They're standing still. There is no force acting on them at all.
Brian Cox, there is no force acting on them at all.
Gravity is not a force, but you can think of it as a force. Maybe that's the... Now, literally, it's not a force.
George Musa, 2019. It is literally not a force. From Wikipedia, gravity is most accurately described by general theory of relativity, which describes gravity not as a force. From Universe Today, in general relativity, gravity is not a force. From physics.org, according to this theory, gravity is not a force. From Physics Info, from the Physics Hypertextbook, gravity isn't a force.
This video is all about Albert Einstein. Yes, that guy again. Einstein is famous for his theory of general relativity. It's taught us that gravity is not a force. And that's probably the most misunderstood physics fact ever. Like, even physicists get it wrong all the time. Gravity is not a force. And since there's no force pushing down on you, that means you're currently accelerating upwards. Unless you're watching this from the ISS, in which case, please say hi to the moon. How does gravity work if it's not a force? That's what we'll talk about today. An accelerometer is a device that measures acceleration. If you'd hold an accelerometer steadily in your hand, it'd tell you it's accelerated upwards. This isn't hypothetical, weird, theoretical physics talk. You can buy one and just see what it says. This is an example of how the reading of an accelerometer looks like when it's lying still on a table. It tells you it's accelerated upwards. And this is entirely correct. If you hold an accelerometer still on the surface of Earth, it's indeed accelerated upward. Why does that surprise you? If you hold something on your hand, you feel that it's pressing against your hand downward. It's like when you're trying to accelerate a car with your hand. It'll push against it. If you hold something in your hand, that's not the gravitational force pushing it down, because gravity isn't a force. It's pushing on your hand because you are accelerating it upward. Why is the thing in your hand accelerated if you don't move your hand? It's because you are accelerated, and you are accelerated because there's a force pushing on you from below. That's the floor, or rather the atomic bonds in the floor and in the ground below. You see, the entire Earth has internal pressure, otherwise it'd collapse. That pressure generates a force on everything on the surface. And as Newton taught us, a force creates acceleration. So that pressure of Earth creates a force which accelerates you on the surface. But wait, you may say, there's also the gravitational force pushing down. So the two forces balance to zero, right? No, because gravity is not a force. Gravity is a consequence of moving in a space-time that's been curved by the presence of masses. If there are no masses nearby to curve space-time, it's flat.
First off, if you didn't notice from the first video, gravity does not affect anything down here on Earth and is only trying to explain the path of the luminaries above, i.e., the sun, moon, stars, and solar systems in the heliocentric model of our universe. I will once again show former physics professor of MIT for 4 decades, Dr. Walter Lewin, explain this in simple terms.
So what holds our world together? Well, on the nuclear scale, 10 to the minus 12 centimeters, very important are the nuclear forces. On an atomic scale, up to thousands of kilometers, it's really electric forces. that hold our world together. But on a much larger scale, planets and stars and the galaxy, it is gravity that holds our world together. And now you may say, that's very inconsistent with what you just told us, because didn't you tell us that D cancels if you compare gravity with electricity?
Yes, but keep in mind that most objects in the universe have only a very small amount of charge per unit mass. The Earth and Mars have each a charge of about 400,000 coulombs. The gravitational force between them is therefore about 17 orders of magnitude larger than the electric force.
So even though our immediate surroundings are dominated by electric forces, including your own body for that matter, the behavior of the universe on a large scale is dictated by gravity.
As you heard, the professor state quite plainly it is electricity that holds our world together.
On an atomic scale, up to thousands of kilometers, it's really electric forces that hold our world together.
See? Then he stated that not until referring to moons, planets, and stars does gravity take effect.
But on a much larger scale, planets and stars and the galaxy, it is gravity that holds our world together.
Any physicist worth their weight in salt knows that the electric forces here on Earth are 1,000,000,000,000,000,000,000,000. You know what? I lost count. Too many zeros. So we just say 10 to the 26th power. Anyone arguing about Newtonian or Einsteinian types of gravity are only speaking about the lights in the sky, or are over 150 years out of date, as this was well understood when Maxwell wrote his equations. This was the reason the ionosphere was created over 100 years ago, with no test to show it even possible to occur, how they claim. It is clear that many of us who were not educated much further than high school in physics were never taught this at all, and makes me wonder why they would tell anyone gravity holds them to the earth. That was one part of the first video that some had overlooked and I thought was crucial to see. This is taught in the mainstream, high education curriculum, and is not something new we are sharing. Now that we have that out of the way, I would like to apologize once more for leaving out the acceleration part of the topic, as it is one of the most important parts to help us comprehend that there is a vector or downward bias here on Earth. Remember, a vector is an indicator showing what direction matter will go depending on the surrounding electrostatic field compared to its own electrostatic charge, and at what potential it will travel. Here on Earth, we have an electrostatic gradient in the atmosphere that rises in potential the further you get from the surface. The potential grows 100 volts every meter linearly as you rise from the plane, which indicates we are between two Gaussian surfaces. This you may remember from the first video, but what I left out was that only in one direction do things accelerate. Comprehending this is key to seeing the bias in direction. The only direction that matter accelerates naturally and with no outside force made by an animal, plant, or mineral is toward the Gaussian surface with less potential, better known as Earth. This acceleration is very weak at small distances, yet can be very destructive at large ones. The distance we are concentrating on is a vertical one, along the vector created by the Earth's electric field. Imagine dropping a bowling ball onto a couch from around 6 inches. It would make an indentation into the cushion, coming to rest in the center, and the couch would be in good working order after you lifted it off. Now we will drop the ball from around 10 feet up. And instead of the ball remaining on the cushion, it might now bounce off due to the potential it had when it made contact with the couch, causing a much larger reaction of the cushion and springs beneath. It gained this potential because it traveled longer along the vector line that caused it to accelerate. Last, we will drop it from an airplane. Not that I have tested it, but I doubt the couch would be much use as a furniture piece after the bowling ball came to rest, wherever that may be. Probably a few floors below the couch, I would bet. Now someone might claim a helium balloon does not succumb to these accelerations. But if you remember in the first video, this acceleration is very weak, and potential differences of other phenomena such as temperature, gas pressure, and buoyancy are much stronger. If one places a helium balloon in a vacuum chamber where it is more dense than the surrounding area, it most certainly shows it is affected by the downward bias. Outside the chamber, the balloon will rise, but not at an accelerated rate. The same with air bubbles underwater released by a diver. They do not accelerate up but are displaced by the water, which is more dense and therefore the matter in the area most affected by the downward bias. It doesn't keep accelerating up because the water around it only needs to travel the distance of the bubble before the potential is equalized again. The process is then again repeated with the water just above the bubble until it reaches the surface and there is no more water to displace it. Last off, I have heard some state the ideal gas laws disprove electrostatic acceleration on gases, and I must admit it makes me chuckle a bit. Here's a high school teacher explaining why they have to do this and that it is a make-believe place.
There are an uncountable number of molecules inside this balloon. It's my breath. But whatever the gases are inside of here, guys, this is absolutely chaotic. It defies study because it's so complicated. You get the idea? So guys, the question is, how do we fix this? And the answer is, we go to the land of make-believe. And guys, this is not stupid and this is not dumbed down. This is smart science. If you've got a system that's so complicated that you can't study it, what do? You simplify the system. And guys, that's what ideal gases are. Ideal gases are simplified gases that make our lives easier. Now guys, be clear. Do ideal gases really exist? No, but we treat them as if they exist. And what allows this to be the case? Don't write this down.
I hope this may have cleared up any misconceptions you may have had on the matter, or at least help further your comprehension of this phenomena.
The following explanation is adapted from Nobel Prize-winning physicist Richard Feynman's lecture on physics, a section called Electricity in the Atmosphere. For every meter you go up in the air, the voltage increases by around 100 volts, or we could say around 100 volts per yard. We can draw these voltage increases using what are called equipotential lines. Notice that the ground is negative and the sky is positive with respect to each other. According to Feynman, this extends upward to 50 kilometers, or 31 miles, where the air is very conductive. This is the case in fair weather. In stormy weather, like a thunderstorm, things are quite different, and I won't talk about that here. But if this voltage exists between your head and the ground, why don't you get a shock? The reason is that your body is a good enough electrical conductor that standing on the ground, you're basically a part of the ground. The equipotential lines would look like this. There's still effectively 0 volts between the top of your head and ground. Similar effects happen with trees, buildings, and so on. What about the electric current? The downward electrical current exists and consists of positive ions, molecules or clumps of matter that have a positive charge. These ions are moving slowly toward the ground. The current density from these ions is very small, around 10 microamps or 10 picoamps, crossing each square meter or yard every second. So in any small area, there's not a lot of power. And that's the explanation about atmospheric electricity adapted from Feynman's lectures. To take advantage of this atmospheric electricity, we electrically connect one end of a wire to the ground and lift the other end up into the air. In our case, we got good results at around 120 meters or 390 feet up. At 100 volts per meter or 100 volts per yard, that's 12,000 volts between that height and the ground. But just as with you standing on the ground, the wire is an electrical conductor, and so is also at ground potential. Looking at the equipotential lines around the wire, that voltage of 12,000 volts exists between some distance away from the wire and the wire. You can see that the equipotential lines are closest together at the top of the wire. This means the attraction is strongest there, and electrons make their way upward in the wire. Let's look more closely at the top of the wire. We'd put 6 sharp points using sewing pins at the top of that wire. But for ease of illustration, I'll draw just one. Notice that because of the sharp shape at the point, the charges are crowded together at that point. Remember also that there are positively charged ions in the air. An electric field exists between the negative charges on the wire and the positive charges in the air. And we can represent that electric field by drawing lines between pairs of opposite charges. Notice that the electric field lines are closer together near the point, meaning the electric field is stronger there. It's strong enough to remove the negative electrons from the sharp point, where they neutralize positive ions. But due to the voltage, there are fresh positive ions moving downward and fresh negative charges coming up from the wire. We now have electricity flowing through the wire.
Another aspect that should be understood is that in fair weather condition, the atmosphere is predominantly positively charged, whereas in dark cloud conditions, the atmosphere is negatively charged. In both cases, the charge built up seeks to reach the ground. One reason